Hello everyone, and we would like to continue with the last class work where we said that something about the Heaviside unit step function, and in that class I mentioned that the purpose of the Heaviside unit step function is to deal with time shifting or the t shifting property of the Laplace transformation. And before doing the t shifting property, we have already done the s shifting property, and that will happen whenever you multiply an exponential function. Okay, the exponential function can be a at here or a minus at here. If there is a plus a is there, then here minus a will come. If a minus a is here, you have to put a plus a. So that's both are acceptable, and a is in general complex number. So you have the s shifting theorem already there, and similarly we are going to do the t shifting theorem. Only thing is that when we are dealing with the t shifting theorem, we need an additional function called the unit step function. Okay, it is written as h here because it is the Heaviside unit step function. It is also called just unit step function. Otherwise, another symbol for h is u. So there is another name for this h of t minus a, that is nothing but u, and then you put this a as a suffix here and then t here. So that is the same name as h of t minus a. So let us use uniformly h of t minus a in our class, but situations will change depending upon the book that you are going to read. Okay, so whatever that we are going to do, this basic definition has to be kept in mind, that the Laplace transform of the f of t represented in small letters is this integration, which will be finally represented by a capital letter. So based on these ideas, we are now moving on to the t shifting properties of the Laplace transform. And by that, what do you mean is that we are interested to calculate the Laplace transformation of the function f of t minus a, which is nothing but time shifted. But in order for the time shifting to work properly, we need this Heaviside unit step function to be multiplied by the original function. And the need, and why should you multiply, is what we have seen in the last class. Only when you multiply the original function with the unit step is just 1. We are just multiplying by 1, so nothing will happen to the original signal. The purpose of multiplying this is only to make 0 in some places. So that is the main reason. This 1 is not the point to be noted. Because of 0 only this function is required, and it has to be otherwise in the sense, what do you mean by otherwise is whenever t is less than a. T is less than a. But remember that this integral, there is a t equal to is there. T equal to, by definition, t equal to 0 to infinity. When we say that t is less than a, still it is greater than 0. Okay, so it is greater than 0, but still up to a. That quantity is 0, and afterwards it remains the original. 1 means original. 0 means you are actually switching off the signal. Switching off the signal, switching on the signal. That's all about it. So that's an equivalent, and we will now come back to this, and then we will evaluate this integral based on the definition of the Laplace transform. So by definition means integration. So we will write like this. So let me maybe I'll write here. So this is equal to integral 0 to infinity. First you have to write down the original function. Afterwards you have to multiply by e to the power of minus st. So we can write down f of t minus a, h of t minus a, e to the power of minus st dt. So that is equal to, now what happens is that this function is either 1 or 0. So you have to be careful where it becomes 0. So in that region you can remove it. So what we understand is that from integral 0 to a, because this is up to infinity, right? So this is actually 0 to a plus integral a to infinity. Like that it becomes. Then what happens is, during the region 0 to a, you can see that 0 to a means what? It is the otherwise condition. The otherwise condition, this is 0. That means this quantity is 0. This quantity is 0. So when I am putting a 0 here, the first integration is actually 0. So this is 0. So there is no need to write everything. The totally it is 0. Then after a you have a to infinity. From a to infinity, what is the value? T is greater than or equal to a. That means a to infinity, its value is 1. So therefore when I multiply by 1, this is 1 actually, we will get the original function here. So I will multiply by 1 and write down this. This is equal to f of t minus a, then you have a 1 here, then you have e to the power of minus st, then you have a dt. That's all. So the integration has come down, very easily, and then now we can simplify this expression. So for doing this integration, okay, this is what you have, the integral I here. Anyway, this portion is gone. Now the lower limit is a here, so we would like to convert the lower limit to 0. Okay, the advantage of conversion is that by definition Laplace transform starts from 0. Okay, so therefore we try whether it is possible or not. We have to try. So by trying, we find that it is successful, that we will be able to make the lower limit 0. How do you do the lower limit 0 is that let us consider this quantity t minus a as a new variable t prime, because if t is the original graph paper, t prime means graph paper is shifted. Okay, I don't want to redraw the axis on the same graph paper. I take a new graph paper and then shift the entire graph paper, then that is called a new graph paper t prime. That's how you can understand. But fine, t minus a is a new variable mathematically, and if that is the situation, I get dt would be equal to dt prime. And here when t equal to, this is limits, so for limits it is clear. For limits, if t equal to a, then you have t minus a equal to 0, which means that t prime equal to 0, which means t prime equal to 0. So maybe if that is not clear, I would like to write down here. So you have t minus a equal to t prime, this is lower limit. Okay, so the t equal to a is your lower limit here. That is, this is the t equal to a. So because of that reason, so t prime equal to 0. So now the point is that lower limit is been brought down to 0. So that maybe we are looking again very similar to the original Laplace transform. That is the idea of doing that. And if you do all that, we will be getting the integral I equal to. So the first part is 0, no need to write. The second part is given like this. This is an integral where t prime is 0, lower limit, and then the upper limit is infinity. F of t minus a. So we get f of t minus a is nothing but t prime 1, then e to the power of minus s into. So you have t. So what is t here? T minus a is t prime means how much is t? So t will be equal to t prime plus a. So you can write down like this, t prime plus a. Then you have a dt. Like that you can write, and then you can now see whether e to the power of, this is a integration with respect to t, and you can see that this a is constant, which is independent of t, and s will not be affected by this t. So s into a is a quantity which remains unaffected by the integral, so we can take it out. So I can write down that this expression is equal to e to the power minus as. So e to the power of minus as, then you have the integral 0 to infinity. The rest of the thing is f of t prime e to the power of minus st prime. Sorry, this is dt prime, right? So you have here this one. So we can now write down that this is dt prime. So this is important. How does this look like? This is looking identically same as your original definition. Okay, you should not worry that there is a prime here. For the definite integrals, this is the definite integral, right? Limits are there. So limits are there means definite integral. For the definite integrals, the variable of integration is t prime. The variable of integration is a dummy variable, because it doesn't matter whether you use any symbol. For example, if you are going to do x here 1 to 2, dx is nothing but is identically same as integral 1 to 2 y times dy. So the question is that Is there any importance for the x? There's no importance. Whether it is x into dx or y into dy, we are going to get the same result. Therefore, the symbol x itself doesn't have any weightage. If you don't want x, you can put it y. If you don't want y, you can put y prime. If you don't want y prime, I can put x prime. They are all identically same. Therefore, what happens is, when I am writing like this f of t e to the minus st dt, it doesn't matter whether you write prime, prime, prime. All the t can be replaced by t prime. Still, it is identically same Laplace transformation without any change. So that is the point that you have to understand. Once it is clear that this expression and the original definitions are identically same, which means that you can now write down that this is capital F of S. I am explaining a little bit. The reason is, you may think that shall I write f of S prime? Like that you may get it out because there's a prime here. It is not like that. Okay, so any variable that you are going to use, it doesn't matter, as we have seen as an example. So therefore, this is nothing but it is a Laplace transform of f of t itself. Prime has no importance at all. Okay, that's what I am trying to say. And if that is the situation, we will be getting the result finally e to the power of minus as into, this is nothing but capital F of S. And by capital F of S, you have to understand that Laplace transform of f of t. Every time you have to do this. Otherwise, things will not be clear. And in particular, when you are solving the problem, this remembrance, like f of s is nothing but L of f of t, requires whenever you are taking a particularly inverse transformation. So that's why I am explaining this. And so we got this result. So we got this result finally. So maybe I will write down the final result. This is the result. I will copy it here. Oh, that would be the final answer. So maybe I will erase and write down final result here. So we have the Laplace transform of the function t minus a, which is multiplied by h of t minus a, all that equal to e to the power of minus as. So this a has to come here. So that's how we can easily understand. Once the a comes here, okay, this a comes here, the job of a is over. What do you mean by that is, the effect of a has been taken care by the factor e to the power of minus as. So e to the power of minus as takes care of the t shifting. If a takes care of t shifting, then a is no longer important. We are left out with only f of t, not t minus a. Therefore, you get f of s here. So that is what you have here. You have f of s here. So you have to understand like this. E to the power of minus as takes care of the shifting a. Therefore, the shifting property has been taken care. What is left out is only f of t. And for that f of t, f of s comes into picture because of Laplace transform. If you understand like that, it will be quite easy. And this property is what is called the t shifting property. So we can usually we can solve many problems once you are having t shifting, s shifting, and then the last class work, namely the gamma function and then the power function. Okay, once you have all these things, several combination of the functions, you can solve the problem. For instance, if for example, if you are going to take the example of calculate the Laplace transform of, so you are going to have f of t minus a. So we can say that this is something like cos of 4t minus pi by 3. Okay. Suppose if there is a function like that, we are interested to calculate the Laplace transform of the shifted function, then you have to understand that we can do this transformation provided you multiply by the unit step function. That's important. If you are not multiplying by the unit step function, then this property doesn't come into picture. That's a different problem. Okay, so we have to be careful that you should not close the bracket here. So if you put a close bracket here and then you start doing the integral 0 to infinity, then this quantity, it will not work. Okay, so the purpose of the multiplication is clear, that we are shifting the original graph. Therefore, the meaning will completely change if you forget the h of t minus a. So therefore, naturally what you have to do is, We are interested to find out the Laplace transform of the cos of 4t minus pi by 3. That's what is given. But then how do you understand this is that cos of 4t is my original signal. That original signal is shifted by an amount pi by 3 to the right side. Okay, right side, it is shifted to the right side. That's why minus pi by 3 is there. If this is the original graph and if you are shifting to the left side, then there should be a plus pi by 3 here. Okay, so we are now shifting. So that is what is happening physically. I mean, when you draw the graph or using a signal generator. But in mathematically, this will happen only if you multiply by this Heaviside unit step function. Therefore, you have to multiply h of t minus same amount only you have to put. You cannot put any other number. So you put this pi by 3. That is how you do this expression. Okay, what does this mean? In other way, it is not the only way to write. The other way to write down is that the meaning of this particular function, we can put this Laplace transform later. What do you mean by this is, what is the meaning of this multiplication is that, I will tell the multiplication meaning. This will be equal to, we have this cos of 4t minus pi by 3 if this 4t is greater than pi by 3. Otherwise 0. So we have to consider 4t is the x-axis and then you can plot. So that is how the idea comes. So once this idea is clear, instead of writing if condition, otherwise condition, if you want to avoid all these things will be taken care by h of t minus a. So that this everything is taken care if I write down h function here. So therefore we write like this, h of t minus pi by 3, and that function we are going to take the Laplace transform. And the answer comes in one line. That's all about it. That's why initial understanding is very important, and then once you apply this, you get the answer quickly. So what is the answer here is that the answer is given by e raised to minus as. So I have e raised to minus as is there. So what is that value? Minus pi by 3. Sorry, this is pi by 3. Then you have s here. Multiplied by f of s. But what is f of s here? So this f of s is nothing but, you have to understand that f of s is nothing but L of f of t. That then only it is easy to understand. So therefore I will write down that this is f of t is cos of 4t. So like this you have to write. Otherwise directly if you say f of s, I don't know what is f of s. So f of s is nothing but L of f of t. Then you ask the question, what is f of t? This is f of t minus a. F of t minus a. Then what is f of t means? The minus a you remove. That is this thing. So once you have this, the answer is quite simple. We have e to the power of minus pi s by 3 into Laplace transformation of the cos. We have done all these things in the previous classes. The answer is given by s divided by s square plus a square. So we have s square plus a square is 4 square, which is 16. So this is the answer. So that means I means this is the I. Okay. So if you are going to use the properties, okay, whatever property it is, you don't have to do the integration. And then if you are going to use the important expression, namely the power function combined with the exponential, that will generate these kind of expressions quickly, and therefore the results can be obtained in a few steps. So this is very important, and similarly we will see some more properties like the differentiation property maybe in the next class. Fine.